Today, we'll be looking at Section 3.2. Section 3.2 is about conditional probability. So when we're looking at probabilities of given events, they don't always occur in a vacuum. Oftentimes, the probability of an event can be affected by some other external factor that changes the probability of a particular outcome. So here is an example. The math club is having an election for club president. 5 club members are running for office: Jen, Frank, Peter, Maria, and Stacy. What is the probability that Frank is elected? So with a problem like this, we can't really say for certain that each person has the same odds of being elected, because maybe Jen is very well liked or Frank is kind of hated. All we can really do here is assume they all have an equal chance. And if they do have an equal chance, then the probability that Frank is elected would be 1 out of 5, because there were 5 people running, and Frank was one of those people. But what if, as the election was happening and votes were being counted, what if someone who's counting those votes sent you a text message and tells you that Jen, Maria, and Stacy all lost? What's the probability that Frank is elected now? So hopefully you can see that having this little bit of information changes the probability. Because now there's no longer 5 possible outcomes. We've lost 3 of them. So instead of being 1 out of 5, now the probability that Frank wins is going to be 1 out of 2. So that shows us that knowing a little bit of information can change the probability of an outcome. And this brings us to the concept of conditional probability. Conditional probability is the probability that an event occurs given that another event has already occurred. And the way we write it is P parentheses B with a vertical line, A, and then a parentheses. This means the probability that event B occurs given the fact that event A has already occurred. So B is what we're interested in the probability of, and A is the extra information we have. It's an event that we already know happened. Now that event may impact the probability of B, it may not. But we have to investigate how that works. So here's another example. You have a standard deck of 52 playing cards. You draw 1 card at random, and we're going to answer a few questions. Part A. Determine the probability of drawing a king. And B. Determine the probability of drawing a king given the fact that you know a face card was drawn from the deck. So to answer these questions, it would probably be a good idea to see what a deck of cards looks like. So I have a diagram here. Cards are broken down into various suits. The 4 suits in a deck of cards are hearts, diamonds, spades, and clubs. The hearts and diamonds are red cards, and the spades and clubs are black cards. Each different suit has 13 cards: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Jacks, queens, and kings are called face cards because if you've ever seen a deck of cards, you know that those cards have faces. And let's clear up one common misconception here. Aces are not face cards. They are a different type of card. They're special because in some games they're a high card, other games they're a low card, and in some games they can be both. So now that we've seen what a deck of cards looks like, we can use this diagram to help us answer these two questions. The first question was, what's the probability of drawing a king from the deck? Well, looking at this diagram, we can see that there are 4 kings in the deck out of the 52 total cards. So the probability of drawing a king would be 4 out of 52. Now, whenever we're dealing with probability and fractions, we want to reduce our fraction to its simplest form. So 4 out of 52 reduces to 1 out of 13. And that would be our answer. Part B was a conditional probability problem. So it says, what's the probability of drawing a king if you know that a face card was drawn? So the minute that I know a face card was drawn, that eliminates all the other cards from the deck that weren't face cards. That means there are no longer 52 possible outcomes. There are only 12, because there are only 12 face cards in the deck. So now the probability that I drew a king changes. There are 4 kings in this deck out of the 12 face cards. So the probability of drawing a king, given that a face card was drawn, is 4 out of 12. Again, we reduce, and this becomes 1/3. So hopefully you can see that knowing the occurrence of another event can reduce the size of the sample space. How about another example? At a recent political gathering, attendees signed in, and their education levels and party affiliations were recorded. The gathered data is presented in the table below. One of the attendees is chosen at random to be interviewed. So let's take a look at this table. We can see we have college grads and people with some college or less. And then we have Democrats, Republicans, and Independents. The questions that we want to answer here are, first, what is the probability of choosing a Democrat? And second, what is the probability of choosing a Democrat given that a college grad was chosen? So the first question is not a conditional probability question. It just wants to know the probability of choosing a Democrat. But the second question is a conditional probability question because we have a little bit of extra information. So let's focus on the first question. Whenever we're dealing with probability and tables, it's always a good idea to add up all the rows and all the columns in your table. So if we add up all the Democrats, we see there's 116. The Republicans number 113. And for independents, we get 25. When we add the college grads up, we end up with 137, and those with some college or less add up to 117. So now we're going to go ahead and add. We want to add the numbers on the bottom together, and we also want to add the numbers on the side together. Those two sums should come out the same, because those two sums represent the same number of people. And when we add them together, we end up with 254. That's the total number of individuals that attended this rally. Now we're ready to answer our questions. The first question was, what is the probability of choosing a Democrat? Well, from our totals, we know there were 116 Democrats out of the 254 people at the rally. So the probability of choosing a Democrat is 116 out of 254. Again, we want to be able to reduce this fraction. We can divide the top and bottom by 2, and that leaves us with 58 over 127. And that's your answer to part A. For part B, what's the probability of choosing a Democrat given the fact that a college grad was chosen? So once we know a college grad was chosen, that's really going to change the way that our table looks. Because we know that we didn't choose anybody from the row that says some college or less. So we can eliminate that entire row. But that also eliminates the 117 number, because that number came from the some college or less row. But we also eliminate several other numbers. As a matter of fact, we eliminate any value that was computed using any number from the some college or less row. So that includes the 116, the 113, the 25, and the 254. So all those numbers go away. Now our entire universe is just the college grad row. There were 137 people at this rally who were college graduates, and it's broken down into 47 Democrats, 82 Republicans, and 8 independents. So the probability of choosing a Democrat from this group of college grads is going to be 47 out of 137. And that fraction doesn't reduce, so that's your answer. So we have a little note here. When using tables to compute conditional probabilities, the condition just eliminates part of the table. We can see that from the problem we just did, where we eliminated the entire row of people with some college or less. So now, how about a practice problem? A certain type of flower comes in 3 colors: red, white, and pink. There are also 3 possible petal arrangements: 3 petals, 5 petals, or 8 petals. 1,000 of these flowers are chosen at random and classified. The results are presented in the table below. So we have 107 3-petal white flowers, 174 3-petal red flowers, 63 3-petal pink flowers, and so on. Then we want to ask 3 questions. First, if we choose one flower at random, what's the probability that the flower we chose was white? Second, what's the probability that that flower we chose was white, given the fact that we chose a 5-petal flower? And third, what's the probability that the flower has 8 petals, given the fact that the chosen flower was red? So go ahead, pause the video, give this a try, and when you're ready, press play. Okay, so let's take a look. Again, since we're dealing with probability and a table, we want to add up all the rows and columns. So if we add up the white petal flowers, we get 248. For red petal flowers, these add up to 403, and pink flowers add up to 349. 3-petal flowers add up to 344. 5-petal flowers add up to 283. And 8-petal flowers add up to 373. If we add the row values together, we should get the same as if we add the column values together. And they both add up to 1,000. So there were 1,000 total flowers here. Now we're ready to compute the probabilities. The first question was to find the probability of choosing a white flower. This is not a conditional probability. So how many white flowers were there out of the total number of flowers? According to the table, there were 248 white flowers out of 1,000 total flowers. That means the probability of choosing a white flower is 248 out of 1,000, which if we reduce, we get 31 out of 125. And sometimes we like to express our answer in decimal form. So if we did that here, it would be 0.248. That's the answer to part A. For part B, We want to determine the probability of getting a white flower if we know that a 5-petal flower was chosen. Once we know that a 5-petal flower is chosen, that means that the flowers that were 3 petals weren't chosen, so we can cross that off, and the flowers that were 8 petals were not chosen, so we can cross those off. We can also cross off the 344 and the 373 because those were the sums of the crossed off rows. In addition, we should cross out any value that was computed using a value from a crossed out row. That would be all the numbers across the bottom. Those go too. So now our entire universe is just 5-petal flowers. There were 283 total 5-petal flowers. And the question is, what's the probability of choosing a white flower from this group of flowers? Well, there were 42 white flowers out of the 283 5-petal flowers. So the probability of choosing a white flower, given that the flower had 5 petals, is 42 out of 283. That fraction doesn't reduce, but we can convert it to a decimal, which would be 0.148. For part C, we'll go back to the unadjusted table without any rows or columns eliminated. And in part C, we want to know the probability of choosing an 8-petal flower if we know the flower that was chosen was red. Once we know the flower chosen was red, we know that it wasn't white and that it wasn't pink. So we can eliminate the columns that came from white and pink. We can also eliminate the sums from those columns, 248 and 349. In addition, we can eliminate all the sums along the right-hand side because those were computed using values from the eliminated columns. All we're left with now, our entire universe, is red flowers, 403 of them. So when we look at the 8-petal flowers from this group, there were 82. 82 8-petal flowers out of 403 red flowers. So the probability of choosing an 8-petal flower, if we know the chosen flower was red, is 82 out of 403. Again, this is a fraction that doesn't reduce, but as a decimal, it's 0.203. And that's your answer to part C. So now, let's take a look at another example. You flip a coin 2 times. What is the probability that you get a tail on the second flip if you know the result of the first flip was a head? So when we look at this problem, we know that a coin flip has a 0.5 probability of coming up heads and a 0.5 probability of coming up tails. But the real question here is, does the first flip affect what happens on the second flip? Knowing the outcome of the first flip here has absolutely no bearing on the second flip. So that means the probability that the second flip is a tail, given that the first flip was a head, is just the probability that the second flip is a tail, which is 1 out of 2, or 0.5. That brings us to a new concept. Because sometimes events affect each other, and sometimes they don't. Our new definition is the definition of independent events. 2 events are independent if the occurrence of one of the events has no effect on the probability of the other event's occurrence. So, symbolically, the probability of B given A would just be the probability of B. So if 2 events are not independent, then we call them dependent events. So independent means that one of the events has no effect on the probability of the other event, and dependent means there is an effect on the probability. So an example. 2 cards are drawn from a standard deck without replacement. Determine the following probabilities. First, what's the probability that the second card is a queen given that the first card is a king? And second, what is the probability that the second card is a queen given the fact that the first card chosen was a queen? So again, it's a good idea to look back at that deck diagram, and we'll use that to help us answer these questions. So the probability that the second card is a queen given that the first card is a king. So one of these kings is taken out of the deck. And it doesn't really matter which one for our purposes here, so let's just eliminate one right now. Now, when we're asked what's the probability that the second card is a queen, we no longer have 52 cards to choose from because one of the cards was removed from the deck. How many queens remain? And there are 4. And how many cards remain? 51. Those are the numbers that'll come together to make our probability. So this probability is going to be 4 out of 51. And as a decimal, it'll be 0.078. Now let's go back to the deck the way that it was originally with all 52 cards and look at the second part. What is the probability that the second card is a queen given that the first card is a queen? So if we know the first card chosen out of the deck was a queen, then we take away one of the queens from the deck. And again, it doesn't matter which queen we take, let's just take one out. Again, that reduces the total number of cards in the deck. But it also reduces the number of queens. So now there are 51 cards left, but only 3 of them are queens. So the probability that the second card is a queen, given that the first card was a queen, is 3 out of 51. Now, if we wanted a fractional answer, we would reduce this to 1 out of 17. And as a decimal, this is going to be 0.059. So oftentimes, we want to determine the probability of 2 events that occur in sequence. To do this, we're going to use something that we call the multiplication rule. So how does the multiplication rule work? What the multiplication rule says is that the probability that event A occurs and then event B occurs is given by the formula probability of A and B is the probability of A times the probability of B given A. If you think about what we were just talking about as it pertains to conditional probability, this makes a lot of sense. Because if these events are occurring in sequence, event A first and then event B second, we compute the probability that event A occurs, but when we go to compute the probability that event B occurs, we know that event A already did. So that gives us a little extra knowledge, which is why the second probability here is a conditional probability, because we're taking into account the fact that A already happened. We just saw, in the case of that coin flip problem, that sometimes previous events don't have any impact on the probability of the next event. So in that case, if you have independent events, then the probability of A and B is probability of A times the probability of B. We like it when that happens. It makes it much easier to compute. And when you look at this rule, you may also remember back to section 3.1 to our fundamental counting principle and realize that this multiplication rule looks a lot like the fundamental counting principle. And that's because the multiplication rule is the probability version of the fundamental counting principle. So instead of counting the number of ways to accomplish multiple tasks, we're instead computing the probability that multiple tasks happen. So let's take a look at an example. 3 cards are drawn at random from a standard deck without replacement. What is the probability of drawing a king, the 7 of spades, and then a face card? So let's look at that deck diagram again. probability of drawing a king and the seven of spades and a face card. So in that order, we start with the probability of drawing a king. But when we go to compute the probability of the seven of spades, we have to take into account that the first card we drew was a king. So this is now a conditional probability. It's the probability of drawing the seven of spades given that a king has already been drawn. When we move on to the next card, the probability of drawing a face card, now we have to incorporate the fact that two things have already happened. So we think of the probability of drawing a face card given the fact that we've already drawn a king and the seven of spades out of the deck, because those two pieces of information can affect the probability. The multiplication rule says multiply these together to obtain your answer. So the probability of drawing a king is pretty straightforward because it's not a conditional probability. There are 4 kings in the deck out of the 52 total cards, so the probability of drawing a king is 4 out of 52. Then assume we pull one of those kings out of the deck. So let's look at the diagram and just remove one of the kings. Doesn't matter which one. Now the question is, what's the probability of drawing the seven of spades after drawing a king? Well, we know there's only one seven of spades in the deck, and because we drew a king out, there are now only 51 cards to choose from. So the probability of drawing the seven of spades, given that we drew a king, is 1 out of 51. Now for the third probability, we have to assume that this seven of spades is gone now. So let's remove that from the deck. Now, the probability that we draw a face card, since there are only 11 face cards left and only 50 cards remaining in the deck, because we've already taken 2 out, is going to be 11 out of 50. According to the multiplication rule, we multiply all of these together. So if we reduce the 4 out of 52 and then multiply, we end up with 11 over 33,150. And as a decimal, it's pretty small. It's 0.00033. And that would be your answer. So how about a practice problem? There are 20 colored marbles in a jar. 7 red, 6 blue, 5 green, and 2 yellow. You choose 3 marbles without replacement. What is the probability of choosing red, then blue, then red? So this phrase, without replacement, is important. That means that when you pull a marble out, you're not putting it back in. So every time you pull a marble, you're changing the number of marbles available for the next pull. So keep that in mind as you try this practice problem. Pause the video, give it a shot, and when you're ready, press play. Okay, so we've got 20 marbles in a jar. So let's go ahead and start dropping these marbles into our jar until we get all 20 in there. So that's 13, 14. So that's all 20 marbles right there. So now let's put a little space where when we take our marbles out, we have a place to put them. And we're trying to compute the probability of drawing a red marble, then a blue marble, and then a red marble. So when we look in this setup, there are 7 red marbles out of the 20. So when we're computing this probability, we start by computing the first probability, which is the probability of drawing a red marble. Then, when we try to draw the second marble, which is supposed to be blue, we have to take into account the fact that we've already drawn out a red marble. So that's going to be the probability of blue given red. Then when we try to draw the third marble, we're trying to find the probability that that third marble is red But we have to consider the fact that we've already pulled out a red marble and a blue marble. So this is going to be the probability of red given that we've already seen a red and blue marble taken out of the jar. Then the multiplication rule says multiply these values together to come up with our answer. So the probability of a red marble, that's not conditional. There are 20 marbles in the jar and 7 are red. So the probability of pulling out a red marble is 7 out of 20. So let's say we pull this marble out right here and set it down on our little tray. Then we go to try to pull out a blue marble. There are no longer 20 marbles in the jar because we pulled out the red one. And that means there's only 19 marbles left to choose from. Of those 19 marbles, 6 of them are blue. So the probability of choosing a blue, given that we've already taken a red one out, is 6 out of 19. So if we pull out this blue marble and put it on our tray, now there are no longer 19 marbles in the jar. There are only 18. So now the final probability of drawing a red marble, given the fact that a red and blue have already been chosen, we know there's only 18 marbles left in the jar, and now there are only 6 red marbles in the jar. So the probability of choosing a red marble, given that we've chosen a red and blue already, is 6 out of 18. So we pull that marble out and put it on our tray. Then we multiply these together. With fractions here, there's a lot of reducing that can happen. So for instance, the 6 and 18 reduce. 6 goes into 6 one time, and it goes into 18 3 times. Then we can reduce the 20 and the 6 by 2. So that leaves a 10 on the bottom and a 3 on top. But then you'll notice that that 3 on top can reduce with the 3 on the bottom. So we reduce those away, and 3 goes into 3 one time, 3 goes into 3 one time. So now on top, we're left with 7 times 1 times 1. That's 7. On the bottom, it's 10 times 19 times 1, which is 190. So this, as a fraction, is 7 over 190. As a decimal, we get 0.0368. So hopefully you can see how this conditional probability works, where we have to take into account what we did in the previous action when we're computing the probability of the next action. How about another example? You roll a 6-sided die and then choose a single card from a standard 52-card deck. What is the probability of rolling a 2 and then choosing the 2 of hearts? When we take a look at these two actions that are part of this probability experiment, rolling a die and pulling a card out of a deck, they don't impact one another. These are independent events. So we can just compute each probability separately and not have to worry about the probability of B given A. So the probability of rolling a 2 and choosing the 2 of hearts will be the probability of rolling a 2 times the probability of choosing the 2 of hearts. Notice there's no condition on that second probability because these were independent events. The multiplication rule says multiply these together to get the answer. Well, when I roll a 6-sided die, there's only one 2 out of the 6 numbers, so the probability of rolling a 2 is 1 out of 6. To choose the 2 of hearts out of the deck, remember there are 52 cards, but only one of them is the 2 of hearts. So the probability of choosing the 2 of hearts is 1 out of 52. The multiplication rule says multiply these together to obtain your answer. And the answer will be 1 out of 312. As a decimal, that would be 0.0032. Lastly, we want to look at this example. The probability that a cashier makes a mistake on any transaction is 0.02. A cashier makes 5 transactions in a 15-minute period. Calculate the following. First, what is the probability that all 5 transactions had errors? Second, what's the probability that none of the transactions had errors? And third, what's the probability that at least one of the transactions had an error? So, we'll start with the probability that all 5 transactions had errors. So just like we did with the multiplication rule, we can think of slots to be filled in. First transaction, second transaction, third transaction, fourth transaction, and fifth transaction. Now we're assuming that one transaction has no impact on the next and that these are all independent. It would be possible to make an argument that they're not, because sometimes when people make a mistake, it gets in their head and then they're more likely to make another mistake. But we're going to assume that these are independent events. That if a cashier messes up the first time, that doesn't necessarily mean that they'll mess up the second time. So, because we're considering them to be independent, the probability that they make an error on the first transaction would be 0.02. And that would be the same on the next transaction, 0.02. And for the third transaction, the probability of making an error would be 0.02. And it would be the same for the fourth and for the fifth. The multiplication rule says multiply these together to obtain the answer. And this is going to have a lot of zeros in it. It's 0.0000000032. Not very probable at all. For part B, we switch it up a little. The probability that none of the 5 transactions had errors. Well, if the probability of making an error was 0.02, that means the probability of not making an error is 0.98, because those are complements of one another, right? Either you make an error or you don't. You can't kind of make an error. Either you made a mistake or you didn't. So those two probabilities would have to add up to 1. Since the first probability of making an error was 0.02, the probability that you didn't make an error was 0.98. If you think of it in terms of percentages, 0.02 is 2%. So there's a 2% chance that the cashier made an error, which means there's a 98% chance that the cashier did not make an error. So the probability that they did not make an error on the first transaction is 0.98, and then 0.98 for each subsequent transaction. When we multiply these together to obtain our answer, we end up with 0.9039207968. So more than a 90% chance that they won't make any errors. The third question, the probability that at least one transaction had an error, takes a lot more thought. So we're going to look at the transactions and try to figure out, what does at least one error mean? And it turns out that with 5 transactions, there's actually 32 different ways that this can end up when you take into consideration making errors or having a correct transaction. So I'm going to diagram out those 32 different ways for you right now. First, what if there were no errors? What would that look like? Well, all 5 of the transactions would be correct. So that's what this C stands for, correct. So 5 corrects would be no errors. But when we consider the cashier making one error, we really have to ask ourselves, when did they make the error? Did they make the error on the first transaction, the second transaction, the third, the fourth, or the fifth? Each one of those is a different way that this scenario could play out. It gets more complicated when we think of the cashier making 2 errors. Because now we have to put 2 E's in this string. So it turns out there's 10 different ways that 2 E's could be matched with 3 C's. So either the first 2 are errors, or the first and third, the first and fourth, the first and fifth, and so on. 10 different ways that the cashier could make 2 errors. Similarly, for 3 errors, there's also 10 different ways that could happen. And here are the 10 ways that the cashier could make 3 errors, because it depends on when they make those 3. Is it the first 3? Is it the last 3? Is it the 3 in the middle? Or some other arrangement? It's also possible that the cashier made 4 errors. 4 errors is going to look a lot like 1 error. So 4 errors, there are going to be 5 possibilities. Because you can think of having the C basically do the same thing that the E did for 1 error. And then finally, if all 5 had errors, it would just be 5 E's. That's the only way that could happen. So what does at least 1 error mean? At least 1 error means 1, 2, 3, 4, or 5 errors. So all of these different arrangements are the ways in which we could see at least 1 error. At the end of section 3.1, we made a statement. We said that complements would be a very powerful tool for computing probabilities. Because if we wanted to compute this probability, we could find 31 separate calculations for all 31 of those values inside the box. But what complements tell us is that if we take all 32 of these and add them together, those probabilities all have to add up to 1. And so complements say to find the values that add up in the box, we could just do 1 minus the probability of what's outside the box. So that means the probability that at least 1 had an error would be 1 minus the probability that none of the transactions had errors. Because none is what was outside the box, the 5 C's, the 5 corrects. And that's a value we already computed. We computed that value in part B. The probability that none were correct was 0.9039207968. So if we subtract that value from 1, we end up with 0.0960792032. That would be the probability that at least 1 transaction had a mistake. So that brings us to our final note here for the section, and it's the same note that we saw at the end of section 3.1. Using complements is a powerful tool for computing probabilities. It just saved us from having to do 31 separate probability calculations, and instead we got to do 1 minus a single probability calculation. So that brings us to an end of section 3.2. Please look on Pearson for your homework, and have a great day.